As I said in the previous panel, we wanted to do more than just focus on actual predictive performance. We also wanted to encourage people to help other contributors, as we heard about with Gregory Gunderson, and also to take unusual or creative approaches in trying to combine ideas from social science and data science. And so the Board of Advisors of the Fragile Families Challenge reviewed all the submissions, particularly the code and narrative explanation, for the ones that we thought were the most interesting in some sense. So not focusing on predictive performance, but something about these particular submissions caught our eye, and we wanted to highlight them, give them a chance to share what they did today. So our first speaker in this session will have 2 talks, and then we'll have a panel Q&A again. The first speaker will be Nicole Carnegie, who is an assistant professor of statistics at Montana State. And she is also a repeat offender in challenges. So and not only is she a repeat offender, she is a repeat prize winner. So she is the previous winner of the Atlantic Causal Inference Conference Data Challenge. And she heard about this challenge through one of her colleagues and was really excited to join. And we're really excited to hear how she approached it. So, cool.
All right, thank you. All right, well, thank you for having me. This has been just a whole lot of fun all the way through, except for the moments when it wasn't, but we'll talk about that later. And I'm normally a pacer and a gesticulator, but in the interest of the recording, I'll do my best to keep myself over here. So my approach to this challenge was a little bit different in that, not that I didn't want to do a good job of predictive modeling, but I was also trying to think about developing an approach and sort of exploring possibilities and different parameters so that, well, you'll see how it varied from some of the others. So the goal here, oh, I should also say that I was working a bit with Jennifer Hill and a couple of students, James Wu and Rabia Amjad, on this, although in the end, most of it was me, for a variety of reasons. So what we went into this trying to do was develop a black box, quote unquote, procedure that you could potentially apply in a variety of settings without having to do a whole lot of retuning and testing and whatnot. And so the process that I went through had 3 stages: the data cleaning, the variable selection, and the model fitting. The vast majority of the time was in that data cleaning section. So I think I started working on this in April or May, and somewhere around mid-July finally had things in as good a shape as I had decided they were going to get before the end of the challenge, and really dug in on the other pieces. And even so, I would say that I didn't do the half of what I would have wanted to do if I was really doing it right. And I think in this room, I'm a little bit of an anomaly in that I'm a statistician trained by a sociologist, so I have a little bit of the sociological perspective of thinking about the whys and the wherefores and what does all of this mean, but also sort of the data piece and the methodology piece. And so I looked at this and said, well, we've got a lot of missing data, so we're going to have to do something about that. And look at all these skip patterns. Those mean something. And so that was the first thing that I started working on, and ended up being most of what happened with dealing with missing data, which is going through all of the skips in all of the surveys and all of the waves and filling in logical values. So some of them, a question was skipped because they asked, do you have any children other than the focal child? And if they said no, they skipped the next question, which was how many? Well, that's a 0, right? So there's some like that you can figure out. There's others where it was skipped because it was more of a not applicable kind of a situation. And in those, we typically they were categorical, and so we would treat the skip as its own category rather than turning it into something else, so that that group had a particular meaning to it and didn't get filled in. And then some questions where they asked the same question of the same person but in different places in the survey, depending on other context that they were in, and so tried to find those and merge those repeated questions into a single variable that contained all of the information to get rid of that missing data. Also, which I didn't say here, but went through all of the survey questions or the code books to figure out which variables were categorical versus continuous. So I was very intrigued by everybody saying that, well, we just did this heuristic automatic classifier that did so thus and such, and I thought, oh man, that would have saved so much time. But I did it by hand. And so then once those things were done, I would have loved to do something more nuanced with missing data. I think it's really important, but this being a closed endpoint kind of a thing, as other people have said, there wasn't time. So what we ended up doing once the skips were dealt with and the variables were categorized was just doing median imputation for continuous variables and mode imputation for categorical variables. It is what it is. All right, so that's the first 3 months of the challenge right there on that slide. Once that part was more or less taken care of, as much as it could be, we wanted to look at a couple of different things. Obviously, it has been said repeatedly today, there's a lot of variables here. Far more than we have observations, so you got to figure out a way to thin them down. And so I wanted to compare a few different approaches for doing that selection. And so I've seen really just one of these, I think, so far today. Other people may have done similar things. So there's the lasso, which we've all heard about. And then a few competing options. One is a horseshoe prior, one using Bayesian generalized linear models, and then also using Bayesian additive regression trees, all of which will be defined in due course, fear not. And the other thing I wanted to look at was random reordering of variables. And so this was something that I was thinking about. In the data set, everything's in the order that it appears in a survey, right? And the survey is chunked. There's a section about education. There's a section about income. And so it seemed to me likely that questions near each other would be highly correlated. And as has come up previously, these selection methods have different skills in terms of dealing with that situation. And so the thought was, well, it's possible that they would, something like the lasso might do better if I shuffle everything up so that things are less likely to be next door to the same question asked in a slightly different way. And so tried comparing just dealing with the data set as it is versus this random reordering. And then the final thing that I looked at was the choice of tuning parameters for the final predictive model that I used, which was the BART regression tree approach. So for those who aren't familiar with it, BART is, as I said, a regression tree model. So it takes your data and partitions it into subsets on the values of different explanatory variables in order to minimize the variability in your response. So it tries to find groupings in the data that are more similar on the response as a function of different covariates. And it can make splits several deep to build what's called a tree. And then the fit, when you have a tree like this, is just the mean of the subset at the sort of the bottom of whatever splits you have. Nice things about it, it's non-parametric, which means that you can fit extremely flexible functional forms so that we aren't necessarily enforcing something like a linear relationship. You can discover things like interactions and nonlinearities without having to pre-specify them, which was something that I thought might be an advantage of this type of an approach, in that you don't have to have the existing theory there to tell you that these two things should interact. You might be able to discover it on your own. One thing that's nice about BART compared to other regression tree and machine learning approaches is that it is embedded in a full likelihood framework. So you can get uncertainty estimates, variability around anything that you're extracting from this model, which I think in a context of social science in particular is you're not only interested in a point estimate, you're also interested in how that varies across the population. So having some way of measuring variability around things, I think, is important. Right. What you don't want to do here is just have one tree all the way down, and then at the bottom you have your predictions, because that is going to give you, essentially, anytime you have a nested split, that's an interaction. And so if you do everything in one tree, you have a whole lot of interactions and a whole lot of trouble finding, actually, linear relationships, which most models, that's the thing that they're best at. So instead, what the BART does is it does a series of smaller trees where you do maybe 3 or 4 splits, get the predicted values from that tree, subtract them off from your responses, do another tree with 3 or 4 splits on what's left over, and keep doing this iteratively for some number of trees. That number is the main tuning parameter that we looked at in terms of the BART fit. And yeah, it works pretty well. It's worked well for me in other challenges, obviously, as Matt said. So I wanted to see how it would do here. A disadvantage is that with binary outcomes, standard BART is pretty sensitive and a little unstable. So one thing that we have started doing is using cross-validation specifically for binary fits to control some shrinkage in the trees. And that seems to improve performance dramatically. OK. So variable selection. You've heard about the lasso, I think, a few different times, so maybe I won't spend too much time on it. It's you have a penalty term on essentially the sum total of your absolute values of your parameters with some weight on that penalty lambda. In our case, we used a cross-validation approach to choose the value of lambda to reduce error, but not minimize it, because we wanted to avoid overfitting. So it actually takes the lambda corresponding to error 1 standard deviation above the minimum, or standard error. And then we kept anything whose coefficient hadn't been set to 0 as part of this approach. It turns out that this is equivalent to using a Laplacian type prior. So since we're in, oh man, already? We're in a Bayesian framework. It's nice to think about it in a Bayesian form for Bayes. And the other 2 methods are essentially alternate priors, where we're putting priors on our parameters that place different emphasis on different parts of the space. So Bayesian GLM, it's a Cauchy prior, the horseshoe prior. It's called that because it looks like a horseshoe, but you can't actually just write down what it is. So I didn't try. And then finally, because I think that nonlinearities and interactions are important, I wanted to not only use methods for choosing variables that look for linear relationships, and also did sort of an ad hoc approach using BART, where I did a cutoff on the number of times each variable was used in a 1,000 tree fit, and kept those variables which were the most frequently used, and also varied that cutoff to get sets of different sizes. Okay, so in the end, what I managed to do in my 2.5 weeks or whatever that I had was about 100 different combinations that I submitted of variable selection approach, random ordering, yes or no, number of trees, how it was, what the cutoff was. Early on, I did do some using data from just a single wave as sort of a practice run as we're waiting for other waves to get cleaned. So going back to Steve's question earlier of how good is wave 1, I actually have all these on just wave 1, and we could talk about that. And the submission, obviously in line with the requirements of the challenge, were the code that I used and then the predicted values. I thought I changed the slide, but I guess not. So in terms of the final evaluation, we've seen a lot of things in MSE. I preferred to do mine in terms of what I call the standardized RMSE. So you take the square root of your mean squared error and divide by the standard deviation of the outcome that you're trying to predict. And what that gives me is an interpretation now of the value as more or less the average number of standard deviations a prediction is from the true value, which I just find a little bit easier to comprehend than the straight up MSE. So that's what I'm going to show you. The takeaways, some things are just harder than others. So we did better with GPA and material hardship than any of the others, but consistently with the earlier presentation that nothing did amazing, you can see that in general everything's sort of hovering around 1 standard deviation away, which is kind of what you would expect from anything that's normally distributed. So it's not great news. Looking at our variable selection regularization approaches, this has, what do we have? BART without random reordering, BART with random reordering, and then BGLM, horseshoe, and lasso as we go across. And not a whole lot going on there, honestly. The missing tail on the lasso is not because it's way worse than everything else. It is because I didn't get the runs with all of the data submitted using the lasso for selection. So that's where that is. So mostly the ones with all the data are on the bottom and the ones with one waiver on the top. The one thing that did jump out was this number of trees used in the fit. Specifically, the thought is that as the number of trees you're using increases relative to the number of variables you're putting in, you're going to be starting to overfit. And we can see that our prediction error is going up pretty steadily with the ratio of trees to predictors, and then sort of leveling off and seems to do best at actually quite low values in this case. I gotta be careful about generalizing here. So in the end, what I saw was that honestly, the variable selection method didn't make that much difference. The large differences were just on what outcome were you using. There were some differences in the way you did the variable selection, but they're orders of magnitude smaller, just minute changes in terms of the number of standard deviations. But the tree to predictor ratio was also relatively strong. So big picture, because I wasn't like iteratively creating a model, my last one we submitted wasn't particularly special in any way. It was just one of the many settings. So I went back in to look and see if I took the best performing one for each outcome, where would they have fallen amongst all the last ones? And they're generally a little bit better than whatever one I happened to go in last. And so conclusions, it can work as well as anything did. Obviously, we see that there's some problems in general. I would have really liked to have had to do less data cleaning, which is why I'm really enthused about this metadata project. And then in the future, I want to keep going. I would love to keep working on this. People want to keep working on this with me. That's my email address. I think it's just really exciting. And the thing that I haven't done yet is the hypothesis generation piece, which is taking those fits and discovering which things ended up being most important. That's it.
Our next speaker is Brian Goode. He's a research scientist at Virginia Tech. And he actually, the way that he ended up hearing about the challenge is actually part of one of the formative stories of the challenge. So Duncan Watts and Victoria Stodden organized an event at the Social Science Research Council, which was about roughly how we could make social science more awesome. I think the title was a little different. And one of the participants there was Adam Russell, and Brian heard about it from Adam. So, Brian.
Great, thank you. And before I begin, thank you very much for the organizers of this challenge and this workshop. It's been a really useful, and the end result of what everyone's working for is it's really encouraging that we're putting effort towards that. So what I'm going to talk about today is the submission that Virginia Tech put together. As the leader of the submission, the publication co-authors are Debanjan Datta and Naren Ramakrishnan. I'd also like to acknowledge Dashelle Dyson and Samantha Dorn. They both helped out with some of the question matching I'll describe later. And then lastly, part of this was, particularly the analysis part, was sponsored by DARPA, the NGS2 project. There's two parts of this talk. I'm going to try and get to the first part rather quickly so we can focus on the analysis. But the first part is the method by which we imputed data. So it was really clear early on that there's a lot of missing data. Of all the possible data positions within the matrix, 55% were missing. And there are a number of reasons for that. First off, as mentioned in the last talk, there are within survey questions that were skipped, depending on the pathway one takes to the survey. So what we would do is we would identify those and fill in the questions with the value that was answered. The other thing we did was we realized that sometimes if the father had answered the survey, the mother wouldn't have, or if the mother answered the survey, the father wouldn't have. So we did this, what we call the mother-father cross, and we would take questions that were related across surveys, not all the questions related, but some, and we would fill in the values missing. The last thing we would do is do a cross-year filling in of the data, so imputing. And what that does is we notice that early on there's a lot of participants, and it sort of wanes off as time goes on. And so we would fill in data with mean values across the year for those potential cases. So what this does, on one end, you can view this as sort of a representative caregiver is one way to look at this. Another way to look at it is we're merely fitting the definition of the outcome variables. The outcome variables are defined by the surveys. We just made sure that all the definitions were satisfied as often as possible with the data we had. So there's two ways of looking at it, and the code for doing this is up on GitHub. It's on the submission. One thing that I'll mention, and this is related to some of the work going on at the workshop yesterday, it's an open problem of how to automate this question matching. So here we have this issue where the data set's large enough where it's not the best to do by hand, but it's also small enough where it's difficult to automate as well. You need a lot of data to do this sort of automation task. So one approach that we took was to develop an actual recommender. Like we would offer suggestions based on an algorithm of related questions. Examples are shown here. And as the user in the loop, we would just tell the system whether it's right or wrong. And we would have, and it wouldn't just be a complete threshold. We'd have the system tell us, well, we think this actually might be wrong, but we're going to present it to you anyway, and you can remove the X if you want. So it took some of the burden of the question matching off of us directly and put it more on the computer. But it was the best sort of intermediate step that we could think of in the time frame to address that particular problem. But it's still something that's of issue, not just here, but across many domains. This is something that deserves a lot of research time. I'm not going to describe the particular variables in the modeling techniques. I feel like that's been addressed quite a bit so far. I will say, though, we used a lasso where we could, and oftentimes we would construct the variables based on the definition of the survey outcome questions. And we applied them to just a general linear model. That's what we chose. And the results we show in this table here, we analyze both on MSE, the model ranking within the group, and then we look at the baseline error and improvement from the baseline, as well as the elasticity, which that's a measure we came up with to show how between the intermediate and the final steps of the competition, so the leaderboard to the final holdout, how did our model shift with the baseline shift? So how much does the model act like a baseline? And the model we found that was the most differentiating of the bunch is material hardship in terms of rank performance and not necessarily being elastic or representative of a baseline. So let's discuss the analysis. This is a part I really enjoyed about this project because it gave us a chance to really look at error and how we interpret it. So on this slide here, I present this chart is the error, the MSE errors of all the material hardship categories from the Fragile Families Challenge website. And if we ignore everything else, our submission is the green line. It's the Virginia Tech submission. If we ignore nothing else, the MSE score it would seem low, but really we can't say much about it because it's just it's a unit. We have to have a basis of comparison. So we can add in the baseline, which is the black vertical line. The baseline was developed by the challenge, and it's the mean values of the outputs is used to calculate the baseline. All the other submissions are shown in the blue histogram. And so we look at ranking, and we look at the MSE compared to baseline, and we see an improvement. And also within the competition, we didn't perform the best, but not bad at the same time. So we would think that, well, this model should have some value to it. It would be good. So I'm going to show this other case we ran then. And this histogram shows all of our output values on the training set. So we can only do this comparison on the training set without the test data set. And the blue histogram shows all of our output values in material hardship for our own model. And the black lines represent the definition of material hardship. So as mentioned earlier in the presentation, there's really only 12 possible values of material hardship. And so those black lines are the threshold of those values. If we're going to predict material hardship as defined, those would the threshold would be. And we'd be wrong around 69% of the time. And so what's interesting here is, how do we interpret this model? And the difference really is the application by which we're applying. And so what really got us thinking is we need to start thinking about the application to be able to reason about the error. How are we going to use this? What are the forthgoing examples? And so it really started to get us to think about, well, what's really going on here? We boiled it down into correspondence, error, and then the application that we want to use it. So correspondence means, are we taking our model outputs and are they going to represent the actual outcome variable? So for example, our material hardship model, by admitting in the MSE error as our basis of ranking models, we're not required to define based on the material hardship definition. We can choose intermediate values. Same thing for the binary outcomes. We could choose a probability instead of the actual value. Now there are methods, of course, to do this. Ordinal regressions are one way. There's ROC curves for the binary outcome cases for analyzing this. But for material hardship, it was very interesting because we could choose whichever binning threshold we want. And why would you even choose a binning threshold? Well, we have to act on it. So if we're going to, for example, if we're going to use this for inference, we might have very low thresholds. Or if we're going to use this for policy, if we're going to say, for group A with this material hardship category and group B with this material hardship category, we're going to apply two different types of interventions. So that's a threshold on the output. Those are two different bins, and it can be any number of bins. In this case, we have uniform binning, because I'll present some calculations later, and it helped us just to get started with uniform binning. And so we found, though, that we can look at this problem in terms of metaphor to kind of present a different angle of what we're discussing here. The first is we can take a machine learning metaphor for our models. And the metaphor is we treat machine learning models like a student. We train them, and then we test them, and we send them out into the world. Or they run away. I don't know. It depends. Grad school, But there's a correspondence criteria. The output of that model is meant to correspond to the outcome variable. And this is difficult. That's a constraint on this whole process. So let's now take the view of analysis, the boundary of analysis, off the model and towards the whole process. There's another metaphor that we can apply. It comes from more of a control theoretic viewpoint, and also I reference Edwin Hutchins' book, Distributed Cognition. He discusses this too. And it's looking at how does the whole process of what we're trying to achieve, how can we measure that, where the model is just a constituent component. It's a one controller within it. So for example, if you're controlling an airplane, I mean, there's adaptive neural networks in controllers. But you're not necessarily looking at the exact output of the controller. You're looking at how is the plane behaving on its overall course. Now, granted, there's constraints at the controller level. There's definite constraints, but the measurement of utility is at a broader scale. Now, the problem here in social science is, well, these are very complex systems, and we don't always know. So what can we do? Can we actually come up with some way of varying the threshold boundaries that we apply, that we would group on for a result, And can we produce such, at the bottom, this distribution of individual errors, individual case errors and sample errors based on our aggregate model? Because we don't want to throw away an aggregate error metric like mean squared error. It helps us to rank models. It's very useful for that. It orders the models. However, we want some kind of idea of if we apply this to a system, what will we get at the individual level? In particularly for high consequence systems where human lives are involved. So we did this. We went and looked at methods for doing it. We make a number of assumptions, such as the stability of the overall process for modeling it. But generally, what we do is we take, if I step from behind the podium, are you still going to be able to capture this? Yeah, OK, cool. So if we take, for example, this is for, just an illustrative diagram for 2 samples. The circle represents the mean squared error. The cube represents the thresholds that we're applying. So if we're going to make 5 minutes. So if we're going to make a decision, basically, a threshold decision based on the mean squared error, the error can live anywhere within basically this quadrant of the circle. It's all symmetric. But if the error if the error has certain conditions, in other words, that the radius or the mean squared error is greater than any one threshold, there's a chance of committing one error or no errors. Or if the mean squared error extends out, you could potentially enter into the region of 2 errors. That's just for 2 samples. As the number of samples increases, the dimensionality of this mathematical metaphor increases quite a bit. So like in our sample, we're at dimensions of 4,000 some odd. So it's like this, but different. And so what we can actually do, though, is sample this surface. And we can get a probability of individual error that we would be willing to accept for a given application. So using Monte Carlo simulation, and this is for n equals 128, just as an illustrative purpose, we can, before we even begin to design such a system, or a model, we can say, well, we want to ensure that our individual error, so the y-axis is the proportion of individual case error, and the bottom is a normalized, think of it as an MSE in threshold criteria. Just it's a normalized variable, described more in the paper. We can choose ahead of time what we're willing to accept as our error. We can say, well, we want to make sure that our models will have 10 out of 100 people be misclassified or misbinned for this policy, or less or more, whatever you're willing to accept. So you have to decide that ahead of time. And then we can create a new baseline which translates to a new MSE that we can apply and say, well, if you satisfy this new baseline, then here's your probability of misclassifying. And that's ultimately what we get after. So what are the lessons we learned from this? First, there is a potential. It hasn't really been explored in as much in depth as we'd like. There's a potential to start shifting how we view models and their correspondence. So we can broaden our scope in terms of how we analyze these overall systems. So we're not analyzing models, we're analyzing whole programs at this point. There's no aggregate error, has no guarantee for individual case outcomes. That's pretty well known. You know, if 50% chance of raining, you carry an umbrella, it doesn't rain. That's pretty well known. But we can start to calculate what that might be based on application. And the other option is, well, one person might ask, why not just look at case outcomes? But that might over-constrain the model, could lead to overfitting. Like I say, there are advantages to aggregate errors, whether it's L2, L1. And then the last lesson we have is, we can actually start to create baselines that are application grounded and not necessarily grounded in the data that we start with. So think of it like this. Typically in machine learning, we start with the data and go forward. Here we start with the application and can start to go backwards. Here we only go halfway to the model, but there's potential to go even further. Next steps on our end. we are actually, as part of the NGS2 program, creating this sort of baseline calculator tool to run this calculation. That's in the works. We do want to, the imputing strategy I mentioned earlier, we still need to test. In the blog entry, I mentioned that it's inconclusive as to the exact quantifiable efforts, but that's something we would like to explore. And then lastly, it'd be interesting to look at some of the multi-scale processes in the survey and then the actions taken. So for example, eviction could be a very quick process, but if a survey question only gathers at the scale of a year, we might not capture all the values there. So it's something we'd like to explore more and how we work on this. So I know it's a quick talk, but there's more information on the imputing strategy at the blog post. We can share these slides so all this is going on. And then GitHub has the code. If we pass publication review, we'll have the Socius publication, and then of course my email. And then there's a lot of other good research going on at the NGS2 program that's worth looking into as well for sort of related topics. With that, thank you. Sure what the background should be.
Cool. All right. Thank you, Brian. Thank you, Nicole. So we have some time for a question and discussion. Yep.
Always, it's kind of one way to look at missing data regardless of kind of proper way you need to place some values. I wonder if you could talk about how to characterize respondents in terms of this is a person who uses a lot, as a person who doesn't have a lot, but he sort of steers some of the complexity. Whether you could kind of some kind of picture to do with the reason missing this and how common it was.
Yeah, I hadn't thought about that. We really got bogged down in the skip patterns, but I think that it is informative if someone goes through half the survey and then says no or refuses to answer any questions related to their relationship status or something like that. So that is an interesting possibility, something that could be useful to look at.
Did anyone exploit that? Did anybody use the number of skipped or missing fields as a?
So you both dealt with missing data, so I'd like to hear how you think about it, and then we'll see if others here tried to, how they addressed it. Because I think a common theme here is the missing data and different ways of approaching that.
So the question is missing data in general.
Yeah, and then particularly, so one approach is to try to, so there's different kinds of missing data. So that's, I guess, the first part to clarify, is that some of the missing data is actually intentional by the skip patterns, and some of it is people who have dropped out of the survey, and then some of it is people who have refused. So some amounts of missing data from each person are informative about the person, like directly if they refuse or don't know. But some of it is potentially informative because it tells you about which skip pattern they took through the survey, but those are potentially quite different. So one approach is to try to impute the missing data by using information in the skip patterns potentially. Another is to say, let's just add up the amount of missing data and use that as a predictor.
So the one thing that's really interesting about this particular data set and competition is that there's a little bit more insight as to the data as a process. So data, behind every data set or datum is a process, even though a lot of times we might view it as more of at a commodity level. And so I know one thing that we took in our approach was to try and consider that process as much as possible. And so most directly, that's in the skip pattern, and reconciling multiple questions within survey that are really asking the same thing and are just skipped because of the process by which the survey is conducted. The other approach would be looking at the family connections and trying. We called it a proximity relation. So if we couldn't get that question answered by one parent, we go to the other or the caregiver, and we try to exploit that as much as possible. But after exhausting all of those options, we just did the typical imputation strategy of we tried mean and then also most frequent value, and that was our approach.
I think overall there's a lot of missing data, but by and large it's skip patterns, and it's also people who just weren't in a wave, so they didn't answer the survey at all. And that was one thing, that there were indicators for this person was interviewed at wave, because I think that is informative, right? If you can't track down one of the respondents, then there's something probably there. So that was in there. Beyond that, counting up how many, if they were in the wave but refused some questions, was not something that I did, certainly. So our approach again was mapping, accounting for the skip patterns, and would have liked to do what you did with across respondents and waves, but didn't. And then it's a pretty simple imputation strategy.
I have a question that comes from the way we impute, which seems to be very different than the way you impute, because you guys are just putting means or a mode in. And social scientists, when we're imputing missing data, we use all the data on the individual to come up with an indicator, and usually run that multiple times.
Yes.
You don't do that in machine learning, or you guys just aren't doing that? Since we don't do that kind of imputing anymore. I mean, social scientists used to in the olden days.
Right. I'll speak for myself at least. I can't speak for machine learning as a field, but it's a terrible way to impute what I did. It is. It's true, and I would have liked to do a multiple imputation approach like you've described, and accounting for information. And I think, given the time, it would probably improve any of our models vastly. But with 12,000 variables and 3 months, it just wasn't feasible. So ideally, I would do exactly what you said.
Yeah, so the strategies you described are definitely used in machine learning. Yeah, there's a number. In fact, in our paper, we cite some of the major approaches that are commonly used related to what you discussed. I'll be so in the submission, a lot of it did come down to time constraint, but I was actually interested to see the performance given only the strategy described, without adding anything else that's more than the mean or the most frequent value, and still seeing the performance increase. I was more in the submission that we're describing. It was more interesting to see the shift from requiring the model to fit the outcome exactly versus just minimizing the error. And by being able to do that without a really elaborate, or without any additional imputation scheme, I thought was very interesting. So that's why it was left the way it was.
Also, we did have one team that did a lot of work on imputing missing data using a variety of strategies. Adana, do you want to talk about what your team did?
Sure.
Introduce yourself.
I wasn't. So there's a blog post that details the various techniques that they use that I think is published on the website. But basically, what we found was a lot of us were social scientists, and we were reared on the lesson that mean imputation and mode imputation is a bad way to go, and there are better techniques. experimented with mean imputation. Well, we experimented with list-wise deletion, mean imputation, mode imputation, well, just mean imputation, and Amelia as well, so multiple imputation techniques. We weren't able, for computational reasons, to do Amelia on all 12,000, but we had sort of pre-selected the variables that we thought were important and ran Amelia on those. And we found that the technique of imputation didn't make too much difference, which was surprising to us.
On the prediction?
On the MSEs, yeah, on the scores that we
MSEs,
received.
wow.
I mean, that might reflect the fact that we didn't multiply impute the entire data set. We just selected, we had imputed on a trimmed data set. What we did find is that all forms of imputation did better than list-wise deletion. So some kind of imputation was important, but the actual kind of imputation we didn't see much. But that obviously could be, we hope, idiosyncratic. Throw stats out.
But that could be pretty surprising if other people replicate your finding where it doesn't change the MSE much.
Yeah, there were other people who multiply imputed as well, right? I don't know if other people saw the same pattern in their experience.
Other questions? Kelsey?
Sort of a question kind of generally for data scientists, and I apologize if this is just one of those cases that we speak different languages and so I'm missing something. But like a question about timing earlier this morning, I'm a developmental psychologist, and so I'm often interested in change and stability as being very meaningful predictors. And so I'm curious the extent to which these different types of models that have been described today kind of leverage that repeated measures nature of the data, and not just thinking about it as a variable that's correlated highly over time, but rather actually fitting change parameters to that repeated measure and thinking about the extent to which something changes as a meaningful predictor and being used in these models.
I didn't.
So I think that is a great example of a kind of feature or variable that would be potentially hard to discover automatically, but could be created based on theories and ideas about what is actually happening. And I also think that that the metadata itself and made it hard for people to construct those variables. But now that we have questions linked across waves more, I think that's the kind of thing that would be possible in the future.
So since there are a lot of people who thought about the imputation stuff in the room and the skips, when Matt learned about the skips, he said, why are those not just filled in? So if it's a -6 and we know why it's a -6, which is the valid skip code, then why does it not just take the value it ought to take? And then we ran into this problem when we were thinking about how would we implement that, which is that suppose the question is like, tell us the quality of your relationship with the father, asked of the mother, and let's suppose for the sake of argument that this is on a scale from like 0 to 100, it's like a continuous variable. And then it's valid skipped for the fathers who have died. So, like Nicole, you thought a lot about valid skips. How would you deal with that kind of a situation? Or anyone else who's thought about this?
Yeah, that one was the worst. So, if it's how do you feel about your relationship with the father and there's 4 categories, I would leave it as, for those where it's a valid skip because the father had died, I would create a new category for that said, basically this is an invalid question, right? So that they're not being given a value from the other list, but not getting, that it's different. When it's continuous, which I found very few things that were continuous, really, then, I mean, in a sense, you could do something like you have the indicator for whether the father has died, and so make sure you have an interaction in there as well so that they do get some value of 0 or something because the relationship doesn't exist, but then you also allow for differences between those for whom there's no relationship because there can't be or because there isn't. But yeah, those were the trickiest ones for sure.
I have a question for Brian. Two questions, not about the imputation part, but about the second part.
Okay.
The first part. So it seems like one of the arguments that you made in the presentation and the paper that we read yesterday was that for purposes of policy in particular, we might be particularly concerned about misclassification rather than aggregate error. But I wonder whether that is not a point about policy per se, but about certain kinds of policy and certain kinds of intervention. Because you could imagine certain policies might just be continuous or quasi-continuous functions of people's covariates. Like you could imagine, say, a policy that gave cash handouts to people based on their predicted material hardship, in which case it wouldn't really matter if we classified someone as 1/11th material hardship or 2/11th material hardship, but just that we roughly got their level of material hardship. So I wonder if it's actually a more specific point about the kinds of policy that potentially are implemented rather than policy per se. And then the second question I had was whether you had explored the rough correlation between model rank when you look at MSE as your metric of model performance, and if you look at classification as your metric of model performance, misclassification as your metric of model performance, or whether that's just there are too many parameters to say anything particularly interesting about that. But what's the rough, like do models that perform better by aggregate error metrics generally also perform better by this other metric that you're proposing?
Well, the second question, it'd be very interesting to do that. I don't have access to other people's outcomes to be able to do that. But it would be a really interesting study. Sorry?
You will.
I will.
Yeah.
Great. All right. So then that's something that would be very interesting to look at. Okay, so that's for now the first part. Yes. So yeah, I use the term policy in general, and it's given a threshold. Now, the reason for that is this is a starting point to start thinking about the consequential aspects of individual cases, and a lot of policy, such as like tax policy, and that is very threshold-like. So it's a starting point for us, and that's what so that's why we started looking at those bin categories. Now, to extend it, it would require a change in our analysis, but it's certainly possible to start considering the different types of boundary interactions. So instead of the hard threshold, we could consider such as proportional increases based on the variable. So that's something we can look at. I view this as more of like the starting point of this, because the general point, it's not saying all policy in general. I should be more careful about that. You're correct, but it's starting to get us to think about what is it that we want to do with these models. And there's a number of examples where thresholding and binning occurs, whether we consider it or not. And this is one way to start looking at it.
Other questions? Shiva?
Thanks, both of you and everyone. I have a question. As I'm coming from a social science background, and these models can be a bit complicated for me to understand. I guess I wanted to know, how do you end up finding the most important predictors in the models, like to see, is it like for yours, Nicole, for example, is it just the frequency it shows up, or is it, yeah, like, can you explain that whole process? Hypothesis generating?
Yeah, I think that is the downside of the approach that I take, is that piece is a lot more complicated. I can't just look at regression coefficients and p-values and make decisions. So you can, I think a good first pass probably is the frequency, with which a particular variable is used in a tree, because the more often it's used, the more nuance the relationship has. And there are ways for extracting, again, because these are potentially nonlinear relationships, right? You have to do some predictions on like alternate sets of covariates to get a sense for how things change with different variables of the covariate. So it's quite a lot of work. Is the short answer, and it helps to have maybe a couple of ideas going in of things that you want to check and look at.
So the question's on variable importance. I know our team, we mostly considered, well, we used two things. First is lasso to identify the most important variables. And the second thing we used was the actual definition of the outcome variable. So on the Fragile Families website, the outcomes are defined in terms of the survey questions. So we would construct features based on those outcomes. So one thing I didn't mention was, for example, on the outcomes such as grit, material hardship, those are composite. They're composed of several different questions. So we would form a feature that would sum all of the questions together each year. And we'd use that as something we've decided on because it is the question definition. But we didn't do anything beyond on those two methods to select variables.
Any more questions? Okay. It's time for a break. Let's thank the speakers again.